Having studied the works of the ancient Greeks and Romans, Renaissance artists and builders rediscovered the use of a divine proportion used in building extraordinary structures. Also known as the golden mean or golden ratio, the divine proportion is a mathematical formulation exhibited in everything from the logarithmic spirals of a nautilus shell to the structure of a pine cone, from the double helix of DNA to the form of the human body itself. The golden ratio arises from dividing a line segment in such a way that the ratio of the whole segment to the larger piece is equal to the ratio of the larger piece to the smaller piece. For example, we'll divide a line segment of length 1 into two pieces, x and 1 minus x. If 1 divided by x is equal to x divided by 1 minus x, then the division of line segment 1 has produced the golden ratio. Cross-multiply and simplify the ratio to express it as the quadratic equation x squared plus x minus 1 is equal to 0. Using the quadratic formula, x is equal to negative b plus or minus the square root of b squared minus 4ac divided by 2a, where a equals 1, b equals 1, and c equals negative 1. We find the solution to be the irrational number negative 1 plus square root of 5 divided by 2, which is approximately equal to 0.618. The second solution to the problem negative 1 minus the square root of 5 divided by 2 is the negative number negative 1.618. This solution cannot be true in this case because the length of a segment cannot be less than 0. So the ratio 1 divided by x is 1 plus the square root of 5 divided by 2, or about 1.618. This number is often referred to as the golden number and is represented by the Greek letter phi. So why is it called the golden ratio? Martin Ohm wrote the first recorded use of the term golden section in the 1835 second edition of his textbook, Die reine elementare Mathematik. James Sully was the first English historian to use this term in an 1875 article on aesthetics in the 9th edition of the Encyclopedia Britannica. Renaissance architects and artists used the ratio to design many of the world's most famous buildings and paintings, such as St. Mark's Cathedral in Venice, and paintings such as Leonardo da Vinci's The Annunciation. There are many ways to geometrically construct the golden ratio. For example, it appears as the ratio of a side to the base in a 72-degree, 72-degree, 36-degree isosceles triangle. Let's take a look at how this configuration yields the golden ratio. Construct the 72-72-36 isosceles triangle ABC, with AB is equal to BC is equal to 1. An isosceles triangle is defined as a triangle with both two equal sides and angles. Draw a line that bisects angle A and cuts the line segment BC at point D, in which angle A is equal to 36 degrees in triangles ADC and ADB. In triangle ADC, angle D equals 72 degrees, which creates two similar isosceles triangles, ADC and BAC, using the AAA theorem. It follows that the lengths of segments AC, AD, and BD are all equal, which will be called the common length X. The legs AB and BC are equal to 1, which means that CD has a length of BC minus BD, or 1 minus X. Therefore, the ratios of leg to base in triangles ABC and CAD are equal, or BC divided by AC is equal to AC divided by CD. Substituting the values, we obtain the equation 1 divided by x is equal to x divided by 1 minus x, which yields the golden ratio. A golden rectangle is another common construction of the golden ratio. It is phi times as wide as it is high. Golden rectangles are the most commonly cited golden objects in Renaissance art and architecture.